liquid pumping problems work a little bit differently than most other work problems. The reason why they work differently is because most work problems are about moving solid objects, but when we're pumping liquid, each part of the liquid has to move a different height, and we'll see that when we work this example. And what we'll use is we'll use this formula right here, where work is the integral of the work differential. And we'll compute this work differential for every different y value between A and B, where A is the height of the lowest point of the liquid, usually 0, and y equals B is the highest. So we'll work this example right here. We'll have salt water in a conical tank. It's pointed downwards. It has a height of 6 meters and a radius of 3 meters, and it's initially filled with 4 feet of salt water. So let's work on that problem. We'll start by drawing a picture. So here is our conical tank, and it's pointed downwards. And according to the problem, the tank has a height of 6 meters and a radius of 3 meters. I'll draw that like so. So here's the 3 meters, and the height, I'll draw it out here, is 6 meters. And initially, it's filled with 4 feet of salt water. So I'll draw that as well. So at about 4 feet right here, we'll draw the top of the water. It happens here at 4 feet. And what would the radius be? Well, we can actually use similar triangles to figure that out. 3 divided by 4 is the same as, 6 divided by 4 is the same as 3 divided by 2. So that would actually have a radius of 2 meters at the very top of the water. So as I mentioned, we're going to use this trick of letting work be the integral of its differential. And certainly that's true. If you anti-differentiate 1 with respect to work, you'll get W plus C. But the trick's going to be that I need to know a starting and ending Y value, because I'm going to integrate through the height of the water. And then I'll have to get dW in terms of Y dy. So how does that work exactly? Well, I'm going to pick, we're going to start here, and we'll let the A value be 0. So the initial height is 0. And we're going up here to the top at the height of 4. And what we want to investigate is the amount of work to lift this infinitesimally thin cross-section or slab of water up and out of the tank. And we're going to call that the cross-section at value y between 0 and 4. And so here's the few steps that you need to work through. First things first, you need to find the area of the water at that point, and depending on the shape, in this case the shape is a cone, we're going to need to know what the radius is of that circle, because it's a circular cross section. So for this problem, the area is pi r squared, but we need to know what the radius is in terms of y. And of course the height of that particular cone at that point is y. We just said so right here. So what we can do is we can take the fact that 6 divided by y, or we could use 4 divided by y, equals, we'll use 3 divided by r. Because of the similar right triangles here and here, I'll take 6 divided by y equals 3 divided by r. That gets me that 6r equals 3y. And so r is 1/2 of y. So I'll plug that in here. My area is pi 1/2 y squared. So that'd be pi 4ths y squared. Okay, we're going to work our way up to getting the work differential. So before we can get to work, we need to get to the force. To get to the force, we need to know the volume of water that we're lifting. So, well, it's infinitely thin, but we're going to consider just this the differential of volume here. And all you need to do there is just think of this. We have this infinitely thin uh, slab of water, and it has a base area of, we just saw, it's pi over 4 y squared. So actually, in general, let's just say that whatever we got the formula for, it would be the area here. And we were going to multiply that by the infinitely thin dy. This dy we think of as just a very slight, almost infinitesimal change in y, and that almost infinitesimal change in y would thicken this up to a slab of water. And we're trying to find the volume of that slab of water where we just thicken it up by just a little bit of y. All right, so we're going to take this area formula and plug it in for that a. We get pi over 4 y squared dy. Okay, and so that tells me my volume differential. Now, to get to the work, I'm going to need first to figure out the force differential. How much force would be required to lift this volume of water up the appropriate distance? And so let's see here. We need to know basically the force here, like all other work problems, is equal to the weight of this slab of water. And so what I'm going to do is I'm going to take the density, rho, and multiply that by the volume differential. That's the Greek letter rho, and we use that to stand for density. All right, and according to the problem, salt water weighs 10,000 newtons per cubic meter. We are dealing in meters, and so the density would be 10,000 and volume is measured in cubic meters. All right, so I'll take this dV and I'll plug that in right here. And so my force differential will be 10,000 times pi over 4. I'll wait to simplify this until later. Over pi over 4 y squared dy. All right, so we've gone from area to a volume differential to a force differential, and now we're finally ready to figure out what the work differential. Essentially, all we want to know is the work required to lift this infinitely thin slab of water up and out. And work, as we all know, is force times displacement. So we're going to need to find the height that we need to displace that water. That would be this distance here, h. And we're going to multiply that by the force differential. That's the weight differential, if you want to think of it that way. To lift this slab of water, it has weight dF up a distance of h for the height. Now, what else do we know here? Well, we know that this whole distance here is y, and we know that the total distance here is 6. So essentially, the height that we need to lift this water at height y, the further height that it needs to go to get out would be 6 minus y. And that way, the height that it starts at plus the height that we lift it is equal to the total height of the cone. And so I'll replace the h with 6 minus a y, and that'll be multiplied by the force differential. So I'll plug that in. We'll plug in, we got 10,000 times pi over 4 y squared 6 minus y dy. That's exactly what we want. So now we've got our work differential, and we've got it in terms of y times dy. So we'll plug it back into the formula. So work will equal the integral, and we saw that a is from 0 going up to 4. Remember, you want to take, we're integrating over the water itself. So we're going to start at the bottom of the water to the top of the water, 0 to 4. And we'll plug in our work differential formula, 10,000 pi over 4. And I'll go ahead and multiply out that y squared here and here. So that's quantity 6y squared minus y cubed with respect to y. Okay, so let's see what we can do here. We'll factor out the constants, 10,000 pi divided by 4. And then we'll integrate. 6y squared becomes 2y cubed minus, we'll get 1/4 y to the 4, evaluated from 0 to 4. Plug in the top minus the bottom. Plug in the top, we get 64 times 2 is 128. We'll get 4 to the 4th, divided by 4 will be 4 cubed, which is 64. And 128 minus 64 is 64. So we have 64,000 times pi over 4. And now I'll finally divide in that 4 to get 16,000 pi. And that'll give us the work required to lift the entire amount of water from its current location out to the edge of the top of the cone. And remember, the trick to doing these water problems is always not to use the normal work formula, but instead to use this differential work formula. You compute the differential work by starting with the area of a cross-section of water and then thickening it up to get a volume, multiply by density to get the weight, and then multiply the weight by the height that cross-section of water requires to get out of the cone.